So as we get more into three-dimensional figures here, most of the time what we're interested in is the volume or how much capacity these objects have. So what we want to do first is start off very simple with a rectangular prism here. We know you're probably most familiar with this formula, length times width times height, and that is if you have a rectangular prism. But the reason, I just want to derive the reason for it because it's going to be helpful when you do other prisms that aren't quite as simple. So the area of the base of this box, if I take this 8 by 4, that base area would be 32. What happens is, as I raise that area up, you can think of it as layers. So if the height is 5, think of it as 5 1-inch layers. And how many of those layers, or how big would each layer be? So it's 32 square inches times 5 layers, and that's where we get 160 inches cubed. So if you can think of it as the area of the base times that height, you're going to end up being able to apply this to other kinds of three-dimensional figures. So the volume of a right prism, whatever that prism is, you're going to figure out the area of the base and multiply it by the height to apply layers to the base area. All right, so that capital B is going to stand for base area. So if we have a prism with an equilateral triangle, 6 by 6 by 6, the height of the prism is 8. What's the volume of the prism to the nearest cubic inch? All right, so let's think through this about how we might go about this. When I look at that triangle on the bottom, I need the area of that triangle, and it's a 60 degree, 60 degree, 60 degree triangle. So I could draw a height and calculate 1/2 base times height, but I think it might be more efficient to calculate the area of that triangle using our sine formula, because this is an oblique triangle. There's no right angles in it right now. So if I just use 2 of those 6's and the 60 degrees between them, this is 1/2 xy sine theta. I can get the area of that triangle. And then what this is showing is 8 layers of 15.59 inches. That's really what it means. So if I multiply that area of the base that I just figured out times 8, I get my volume to the nearest cubic inch. So try to get the area of the base as simply as you can. And a quick comment on the bases. It's obvious when they're laying like this with a triangle on the bottom and a triangle on the top, but sometimes they are on their side. And so you need to know that the bases are always going to be those congruent parallel figures. So you just need to locate those wherever they are in the diagram. Try to find the 2 congruent faces. Those are your bases. Do the area and then multiply by the height. Okay, so then exercise 3. Cylinder is a solid that follows the same rules. Yes, we've talked about how cylinders are like prisms in that way. The thing is, this if you figure out the area of this circle, all you need is the radius for it. And so the formula for a cylinder is pi r squared h. But it is still capital B times h, because pi r squared is the area of the base. So you're basically using the same formula. You're just applying the area of a circle. So when you look up volume of a cylinder, this is what you'll find. You won't find capital B times h, because it's not really a prism. But you can think of it like a prism and do the area of the base, which is pi r squared, and multiply by the height. So it works exactly the same way. All right, next page. So there's a principle called Cavaliere's principle, which basically says that if you have 2 solids and their cross sections have the same area, meaning the base area is the same on both, then as long as they have the same height, they're going to have the same volume, no matter what you do with it. So a perfect example of this would be a deck of cards. If you take a deck of cards out of the box and just lay them on the table, it's a rectangular prism stacked up vertically. So it would have a volume. You could do the area of one card times the layers, or times the height of the deck, and you would get the volume that it takes up. But if you were to take those cards and slide them off, you could form a parallelogram on the side, right? It would look like a parallelogram from the side, and the volume of that deck of cards doesn't change. It's still going to be the same 52 cards, same thickness and all. So the volume will not change, just the way it's organized. So if we turn a prism into an oblique prism, the volume will not change, provided that the height stays the same. So that's Cavaliere's principle. All right, a non-right prism has 2 square bases. So here's an example of it. The square bases are on the side this time, right? And so the 2 vertical faces that are rectangles and 2 vertical faces that are non-rectangular parallelograms. So the side view is shown here. Determine the volume of the prism to the nearest cubic inch. All right, well, in order to do this, we need to know what the area of those equal bases are. So if I need to find the area of this parallelogram from the side, it's telling me there's a 58-degree angle, but a parallelogram is not base times slant height, it's base times perpendicular height. So I've got to figure out what this perpendicular height is first before I can know what this capital B is. So that's the first thing. I need to figure out the height of the parallelogram. So I take sine of my angle equals height over hypotenuse, right? The h, it would be the opposite side from the 58, and the 7 would be the hypotenuse. So to solve for height, it's times 7. Then I can take that 7 sine 58 and insert it for the height of the parallelogram. Now the base area would be the 4x4 square. So going back to this formula, the capital B stands for the base area, and the height is going to be the height of the parallelogram that we see here. So we end up with 16 times 7 sine 58 comes out to about 95 inches cubed. All right, and following to the last problem, we've got a situation here where we're looking at a chicken coop. Chicken coop is shown as a prism with pentagons on each end, so you could call it a pentagonal prism. So if I want to know the volume of this prism, I have to know the area of that pentagon. So I'm going to look at this pentagon from the side view. It's a 10 by 7 rectangle, and then if you look at the top, there's a triangle here with a height of 4 and a base of 10. So the triangle is 1/2 base times height, or 20. The rectangle is 10 times 7, or 70. So that means that my base area should be 90. The height of the prism is 12. That's the connective rectangle between the two pentagons. And so the volume of this thing would be 1,080 cubic feet, or feet cubed. And so to figure out the last part of it, how many cubic feet per minute must the fan move in order to get all the air out of the coop in an hour? All I want to do is divide the cubic feet by the minutes in an hour to see how many feet cubed per minute I need to move. So this 1080 divided by 60 divides the total cubic feet in the coop by the time that I have available, which is the 1 hour, and it's going to need to be moved at a rate of 18 cubic feet per minute, which might inform me as to what kind of fan I need to get, what kind of setup I need to have in order to make that happen. So the takeaway from this whole section is volume of a prism can be calculated as area of the base times the height, where the base area would be the two congruent figures that are parallel to each other, and the height would be the length between those two. So a lot of times you have to separate it and do that area first, and then you can insert the height to find the total volume.